In this video, I'm going to introduce a process called logarithmic differentiation. The calculation of derivatives of complicated functions involving products and quotients or even powers, it can be simplified using our knowledge of logarithms, believe it or not. And this method that I'm going to show in this example is called logarithmic differentiation. So it's just a process that we can follow to take the derivative of really complicated functions and make the derivative process a little bit simpler. So in the beginning, the first step, we want to replace f of x with y. So I'm going to do these steps as I work through this example. So if your function had been written as f of x is equal to some quantity, then you would go ahead and replace the f of x with y. It's just easier to have it read y equals. And then we're going to take the natural log of both sides. Now, you could technically use any type of logarithm, any base that you want, but the reason why we use the natural log is because later on, when we work on the actual differentiation and we take the derivative of natural log of x is 1 over x. It's a nice, clean derivative. It's a little bit cleaner than, say, the derivative of log base 10. So that's why we're going to be taking the natural log of both sides. So that's going to be the natural log of y, and then we'll take the natural log of this entire ugly quantity. I made this one as ugly as I could possibly think of. So the natural log of this entire thing on the right-hand side. And I made this purposefully really, really ugly because I wanted you to look at this expression, and I did not want you to do quotient rule and product rule and then chain rule. I wanted you to look at this and think, oh, that would be an ugly mess. There has to be a simpler, easier way to take the derivative of something really complicated like this. And that's why we're using this new process called logarithmic differentiation. Now, if you look at the right-hand side here of your equation, you have natural log of this giant quantity. So here's where we're going to use our algebra knowledge, and we're going to use the properties that we know of logarithms to expand the expression that we have on the right-hand side. So there's really not any calculus involved in this next step, but rather we're just going to use our properties of logs. So I see we have this giant division, and we know that division can expand into subtraction. So that would be the natural log of e raised to the x cubed times cosine of x power minus the natural log of the denominator, which is the x to the 5th minus 9x squared plus 3 to the 97th power. And then we'll keep going with our properties of logs. We want to use them as much as we possibly can to expand the right-hand side. So now we notice that we have a logarithm with a product. So we can go ahead and expand that logarithm, and that's going to become addition. So the natural log of e raised to the x cubed power plus the natural log of cosine of x. Then my last logarithm here is raised to the power of 97, and we know that the power rule allows that 97 to come in front and become multiplication. So that would be 97 times the natural log of x to the 5th minus 9x squared plus 3. So right now I have the natural log of y is equal to all of this on the right-hand side. And then we want to just keep looking at all three of these terms and see if we could use any additional properties of logarithms to expand. And we do have a property that we could use right here. And this is our inverse property. So remembering that if we have a log base a, and if the argument is also a base a and it's raised to some power, I'll say the power of b, then the inverse property allows those to undo each other, and we'll just be left with the exponent, the power, which would be b. So in this case, remember, if you have natural log is really log base e, and then we have e raised to the x cubed power. So the inverse property will indeed simplify that, and we'll be left with just the exponent, which in this case is x to the 3rd power. So we'll simplify that. We have natural log of y is equal to x to the 3rd power plus the natural log of cosine of x, I'm going to add parentheses there just to be a little bit more clear, is equal to 97 natural log of the quantity x to the fifth minus 9x squared plus 3. So we have totally exhausted all of our properties of logarithms on the right-hand side. We can't do anything more with that. So now, once we're done with all of the algebra there, now we're on to step 3, and we're ready to do the calculus. And the calculus is we're going to differentiate using implicit differentiation. So we have an implicit equation, so therefore we'll use implicit differentiation, which we know means we're going to be taking the derivative of both sides with respect to x. So we'll take the derivative of natural log of y. But then remember, on the right-hand side, we have 3 individual terms. So we'll take the derivative of each of those terms separately. So the derivative of the first term plus the derivative with respect to x of the second term, and then minus the derivative with respect to x of the last term. So the derivative of x cubed, the derivative of natural log of cosine of x, and then the derivative of 97 natural log of x to the fifth minus 9x squared plus 3. Now you'll notice we're taking 4 individual derivatives, but these 4 individual derivatives are much simpler than taking the derivative of the original equation in its original form. So we've simplified the differentiation by utilizing our properties of logarithms first. And that's the whole idea behind this process. We want to make the derivative part simpler. So on the left side, we're taking the derivative of natural log of y, which would be 1 over y. But then remember, we have to chain on the derivative of y with respect to x, dy dx. Then we have the derivative of x cubed, which is just 3x squared. Now the derivative of natural log of cosine, we have to recognize that we need the chain rule here. So we have the natural log of cosine, whose derivative would be 1 divided by cosine of x. Then we have to chain on the derivative of cosine x, which would be negative sine of x, minus 97 times natural log of that quantity. So that would be minus 97 times the derivative of natural log, which again is 1 over that quantity, x to the fifth, minus 9x squared plus 3. And then we need to chain on the derivative of the inside function, which would be 5x to the fourth, minus 18x. So I'm going to go ahead and clean up what I have here on the right-hand side. So 1 over y times dy over dx will equal 3x squared. Then we have minus sine of x over cosine of x. Now, if you would prefer to simplify that right now, you certainly may. Sine of x divided by cosine of x is tangent of x. So it would be a lot easier just to write tangent, although that's not required, but I prefer that. And then I'm going to go ahead and write the 97 in the numerator multiplied by the 5x to the fourth minus the 18x. And then all of that will be divided by the x to the fifth minus 9x squared plus 3. So the calculus step is now done. Now the remaining part of the process is just to solve for dy dx. So let's go back to our step-by-step procedure here. Step 4, we want to go ahead and solve for dy dx. That was the derivative we were looking for. And then at the very end, we want to write our final answer fully in terms of x. In other words, we're going to be getting rid of or replacing our y. So we're almost done. We just need to solve for dy dx. So to do that, we need to multiply both sides by y, so we can divide out that y. So we're going to have big brackets here, multiplied by y. So now dy dx will equal the big quantity, 3x squared, minus the tangent of x, minus 97, times the quantity 5x to the fourth minus 18x divided by x to the fifth minus 9x squared plus 3. And then that entire quantity is going to be multiplied by y, but we don't want to leave our answer in terms of y. So that very last step is that we replace this y with what y was equal in the original. So if you go all the way back here, here's what y was equal to. So if you can imagine, you're going to take that all the way down to the bottom and you're going to substitute that craziness. And it's going to look ugly, remember, because look at how ugly the original was. You're going to substitute that back in here for y. So here's our final answer. And again, I made this a really ugly example just to demonstrate the process of logarithmic differentiation. But now that you have seen it, it is certainly a process that you're welcome to use if you have a problem where you don't want to do the quotient rule, or you don't want to do the product rule or the chain rule. If something appears to require a lot of different differentiation rules and you want to avoid using those rules, this process of logarithmic differentiation is an alternative for you.